What if the edge of the universe is not a place where space ends, but a point where our scientific intuition begins to fail? What if the very idea of an edge does not exist in the way we have long imagined? And for centuries, we may have been asking the wrong question from the start. In recent years, a series of extraordinarily precise observations has prompted scientists to re-examine some of the most fundamental assumptions about the structure and scale of the universe. Not because a cosmic wall has been discovered at the farthest reaches of space, but because what remains unseen is proving just as significant as what we can observe. These insights are not born from speculation, but from instruments operating at the absolute limits of human capability. Telescopes designed to collect light that began its journey when the universe itself was still young. It is here, at the intersection of technological limits and human understanding, that old questions begin to take on new forms. If we cannot see beyond a certain boundary, is it because the universe truly has an edge? Or because light and time themselves impose a natural horizon? And if there are regions of the cosmos forever beyond our reach, what does that imply about our place within the larger picture? In the journey ahead, we will not rush toward conclusions. If this exploration resonates with you, consider subscribing or sharing where in the world you are listening from. For now, let us take the first quiet step together and begin moving toward what we call the edge of the universe. When we ask whether the universe has an edge, we are not beginning with science, we are beginning with habit. Long before equations or telescopes, the human mind learned the world through boundaries. Every space we inhabit has an ending. A room meets its walls, a house ends at its doors, a road eventually reaches a border, a shoreline, or simply fades from use. Even the ocean, which feels endless when you first look out across it, is known to have coasts, depths, and limits that can be drawn on a map. Our daily experience trains us quietly and consistently to expect that anything real must also be bounded. This geometric intuition becomes so deeply embedded that we rarely notice it. From childhood, we learn to understand space as something container-like. We are inside rooms, inside buildings, inside cities. We move from one enclosed region to another, and our sense of orientation depends on edges being present. Corners tell us where we are. Horizons tell us how far we can see. Without boundaries, our brains struggle to organize experience. Over time, this expectation becomes automatic. Space, to us, is something that must stop somewhere. Neuroscience helps explain why this expectation feels so natural. The human brain did not evolve to comprehend cosmic scales or abstract geometries. It evolved to support survival in environments measured in meters, not light years. Our ancestors needed to judge the distance to a shelter, the edge of a forest, or the reach of a predator. In that context, recognizing boundaries was essential. A cliff edge meant danger. A riverbank marked a crossing point. The ability to quickly locate endings in space was a practical advantage, and the brain became very good at it. As a result, the brain is constantly searching for closure. It looks for endpoints, for conclusions, for places where one thing stops and another begins. This tendency does not turn off when we look at the night sky. When we imagine the universe, the same mental machinery activates. If space extends outward, the mind assumes that somewhere eventually there must be a final edge, a last region, a place where there is nothing beyond. This assumption feels so obvious that questioning it can feel unsettling. But the universe does not arise from the same category of things as rooms or roads. This is where intuition quietly begins to fail. The universe is not an object sitting inside a larger container. It is not floating within a greater space. There is no external frame in which it is placed. When we speak about the universe, we are speaking about the totality of space itself. Asking where it ends is not like asking where a table ends in a room. It is more like asking where the surface of the Earth ends when you walk in a straight line. This distinction is subtle, but it matters. Objects have edges because they exist within a surrounding environment. The universe does not have that kind of outside. There is no observational standpoint beyond it from which an edge could be seen. When we imagine a boundary, we are often unknowingly picturing the universe as though it were an object embedded in something else. That picture feels natural, but it is not required by physics. It is inherited from everyday experience. Space rarely gives us simple answers. There is also a linguistic reason this confusion persists. Words like edge, boundary, and limit are borrowed from familiar settings. They work well when describing furniture or landscapes, but they become misleading when applied to cosmic structure. The language carries assumptions that science does not necessarily support. We say edge because we do not yet have a better everyday word for a limit that is not a wall and not a border, but rather a condition tied to observation itself. Silence is also a kind of data. Once we recognize how much of our thinking comes from habit rather than evidence, the question begins to soften. The problem may not be that we have not yet found the edge of the universe. The problem may be that we are still using tools of intuition that were never designed for this scale. Geometry as we experience it on Earth does not automatically apply to the cosmos. Space does not have to behave the way rooms behave. Distance does not have to lead to a stopping point. Numbers whisper more than they speak. To move forward, we are asked to do something surprisingly difficult. We must temporarily set aside the comfort of familiar mental models. We must allow the possibility that space can be complete without being enclosed, and that something can be finite without having an edge. This is not an act of imagination alone. It is a quiet discipline, a willingness to listen more carefully than our instincts prefer. And perhaps that is where the journey truly begins. Not at the edge of the universe, but at the edge of the assumptions we bring with us when we try to understand it. For most of human history, the universe was imagined as something simple in its shape, even if vast in its size. Before the 20th century, many astronomers and philosophers assumed that space was infinite, flat, and unchanging. It extended forever in all directions, like an endless stage on which matter moved and events unfolded. Time flowed separately, ticking forward at the same pace everywhere, indifferent to what happened within it. This picture felt natural because it aligned closely with everyday experience. When we walk across a field, the ground appears flat. When we look up, the sky seems uniform and calm. Nothing in ordinary life suggests that space itself could bend or respond to what it contains. In this earlier view, the universe was treated as a container. Stars, planets, and galaxies were objects placed inside an enormous, invisible box called space. Gravity acted across that box as a force, pulling masses toward one another. But space itself remained passive. It did not stretch, curve, or react. It simply existed, providing a backdrop for everything else. This idea worked well enough for centuries, allowing scientists to describe planetary motion, predict eclipses, and chart the heavens with impressive accuracy. There was no urgent reason to question it. Then, quietly and without spectacle, that picture began to change. In the early 20th century, a new way of thinking emerged, one that did not merely adjust the old model, but replaced its foundations. Space and time were no longer treated as separate ingredients of reality. They were revealed to be deeply intertwined, forming a single fabric now known as space-time. This shift did not come from philosophy or intuition. It came from mathematics, observation, and a willingness to follow equations even when they led away from comfort. In this new framework, space was no longer an empty stage. It became an active participant. Mass and energy could influence it, shaping its geometry. Time itself could slow down or speed up depending on motion and gravity. Space could stretch, compress, and curve. Gravity was no longer a force acting across distance in the traditional sense. It became the natural motion of objects following the curved paths of space-time. Space rarely gives us simple answers. At first, these ideas seemed abstract, even unsettling. They contradicted centuries of intuition. How could space bend if there was nothing to bend? How could time behave differently depending on where you were? Yet as observations accumulated, the theory continued to hold. Light bending near massive objects, time running more slowly near strong gravity. The slow drift of planetary orbits matching predictions with remarkable precision. Again and again, the universe responded not with resistance but with quiet confirmation. This shift carried a profound implication that often goes unnoticed. If space can curve and evolve, then it cannot be merely a container. A container does not respond to what it holds. But space-time does. It reacts to mass and energy. It carries information about the universe's history. It expands, changes, and shapes the motion of everything within it. Space is no longer the background of reality. It is part of the story. Silence is also a kind of data. As this understanding deepened, another realization followed. The universe is not located within space because space itself is one of the things the universe consists of. There is no external arena in which the universe sits. There is no surrounding emptiness waiting beyond it. When we ask where the universe is, the question dissolves because there is nowhere else for it to be. Space does not exist independently of the universe. The universe is space. This idea is difficult to absorb because it offers no familiar reference point. In daily life, everything occupies a location within a larger setting. A city sits within a country. A room sits within a building. But the universe does not sit anywhere. It simply is. Asking what it is inside of is like asking what direction lies north of the North Pole. The question assumes a structure that no longer applies. Once space is understood as dynamic, the concept of an infinite, flat universe becomes less certain. Space could still be infinite, but it does not have to be. It could also be finite yet unbounded, curving back on itself in ways that do not require an edge. The geometry of the universe is no longer dictated by intuition, but by measurement. Curvature becomes something that can, in principle, be detected, inferred from the behavior of light and matter across enormous distances. Numbers whisper more than they speak. This realization changes how we think about scale and structure. The universe is not a static expanse that has always been the same. It has a history written into its geometry. Space expands. Distances between galaxies grow. The shape of space-time evolves over time. When we look outward, we are not just looking far away. We are looking into a different era of the universe's life. For the human mind, this requires a quiet adjustment. It asks us to release the idea of space as something familiar and solid. It invites us to think of it instead as relational, flexible, and responsive. Not a place, but a process. Not a container, but a structure shaped by what exists within it. As we move forward, the question of whether the universe has an edge becomes more subtle. It is no longer about finding a boundary in space, but about understanding the nature of space itself. And in that understanding, we may discover that the universe does not end the way we once expected, but unfolds according to rules that are calmer, stranger, and more patient than our instincts ever prepared us for. When scientists speak about the edge of the universe, they are usually not describing a place where space physically stops. They are referring to something quieter and more subtle. What they mean, in most cases, is the limit of what can be observed. This distinction matters because it changes the question entirely. Instead of asking where the universe ends, science asks how far information can reach us and why that reach is limited in the first place. The idea of an observable universe emerges naturally once we accept a simple fact. Light does not travel instantaneously. It moves at a finite speed, and that speed is the same everywhere. Because of this, looking far away in space also means looking back in time. When we observe a distant galaxy, we are not seeing it as it is now, but as it was when its light began its journey toward us. The farther the light has traveled, the older the image becomes. Eventually, we reach a point where there has simply not been enough time since the beginning of the universe for light to arrive. This is where the notion of a boundary appears. Not a wall, not a surface, but a horizon defined by time and speed. The observable universe is the region of space from which light has had enough time to reach us since the universe became transparent. Its size is not determined by how powerful our telescopes are, but by how long the universe has existed and how fast light can move. Even a perfect instrument could not see beyond this limit because there is nothing yet to observe. Space rarely gives us simple answers. As measurements have improved, scientists have been able to estimate the scale of this observable region with increasing confidence. Today, its diameter is estimated to be about 93 billion light-years. This number often surprises people because the universe itself is only about 13.8 billion years old. The difference arises because space has been expanding while light was traveling. Distances have stretched quietly and continuously, turning a finite travel time into a much larger present-day separation. Within this observable volume, astronomers estimate that there are more than 2 trillion galaxies. Each of those galaxies contains billions of stars, and many of those stars host planets. The numbers are vast, yet they describe only what lies within our observational reach. Beyond that horizon, the universe does not abruptly change. It simply becomes inaccessible, at least for now. There may be more galaxies, more structure, more variation, extending far beyond what we can see. Or the universe could behave differently at larger scales. Current observations cannot decide the question. Silence is also a kind of data. This is where misunderstanding often enters. The phrase edge of the universe suggests a physical boundary, something one could approach or cross. But the observable horizon is not a feature of space itself. It is a feature of information. It marks the point beyond which signals have not yet arrived. If we were located elsewhere in the universe, our observable horizon would be centered on that location instead. Every observer carries their own horizon with them, shaped by the same fundamental limits. Because of this, the observable universe is not the universe as a whole. It is a sample defined by circumstance. Its boundary is not fixed in space. It expands over time as more light reaches us, even as cosmic expansion pushes distant regions away. The edge moves, but not because space ends. It moves because information slowly accumulates. Numbers whisper more than they speak. Understanding this requires letting go of a familiar image. We are used to thinking of edges as places where one thing stops and another begins. A shoreline divides land and sea. A wall divides inside and outside. But the edge of observation does not divide existence from non-existence. It divides the known from the currently unknowable. It is a boundary of evidence, not of reality. This distinction has practical consequences. When scientists say that the universe is at least as large as the observable universe, they are being precise. They are acknowledging that everything beyond that horizon remains unmeasured. The universe could be vastly larger, perhaps infinite, or it could curve back on itself in ways that keep its total size finite but unbounded. The observable universe does not answer these questions. It only defines the region where answers can be sought through direct observation. There is something quietly humbling about this realization. No matter how advanced our instruments become, there will always be regions whose light has not yet arrived. Knowledge does not expand at the same rate as space itself. The universe grows faster than our ability to observe it, ensuring that some portion of reality remains beyond reach. For the human mind, this can feel unsettling at first. We are accustomed to problems that yield when we apply better tools or more effort. But here, the limit is built into the structure of the universe. It is not a failure of curiosity or technology. It is a reminder that knowing is a process shaped by time. As we move deeper into this journey, the idea of an edge begins to soften. It becomes less about a distant boundary and more about perspective. What we call the edge of the universe is, in truth, the edge of what has had time to speak to us. And beyond that quiet horizon, the universe continues, patient and unobserved, waiting not for discovery, but for light to arrive. When we talk about horizons in the universe, we are not borrowing a poetic metaphor. We are using a precise scientific idea that describes limits imposed not by walls or barriers, but by time, motion, and expansion. Just as the horizon on Earth marks the farthest distance our eyes can see from a given point, cosmic horizons mark the farthest regions from which information can reach us, or ever will. These horizons are subtle, overlapping, and often confused with one another. Understanding their differences helps clarify what scientists mean when they speak about the edge of the universe. The first and most intuitive of these is the particle horizon, sometimes called the light horizon. This horizon defines the greatest distance from which light has had enough time to reach us since the beginning of the universe. Because the universe has a finite age, there is a limit to how far light can have traveled. Even though space itself may extend much farther, only regions within this horizon have been able to send us information in the form of light or other signals. When we observe the most distant galaxies or the faint glow of the cosmic microwave background, we are looking as far back as the particle horizon allows. Beyond it, light simply has not arrived yet. This horizon grows over time. As the universe ages, more distant light has time to reach us, and the observable region slowly expands. In this sense, the particle horizon represents what is not yet seen, rather than what can never be seen. It is a boundary defined by patience. Given enough time, and assuming the universe behaved differently, some regions beyond this horizon could eventually come into view. This idea aligns closely with how we usually think about exploration. There is more out there, just not accessible yet. Space rarely gives us simple answers. The second horizon introduces a more permanent kind of limit. This is the cosmological event horizon. Unlike the particle horizon, which looks backward toward the earliest light we can receive, the event horizon looks forward. It defines regions of space from which signals sent now, or at any time in the future, will never reach us. This horizon exists because the expansion of the universe is accelerating. Some regions are being carried away so rapidly by the stretching of space that even light emitted toward us cannot overcome the increasing distance. This distinction is important. There are parts of the universe that exist right now, emitting light at this very moment, that will never be observed from our location. No improvement in technology can change this. The limit is not practical, it is fundamental. The cosmological event horizon separates what is merely unseen from what is forever unreachable. It marks a boundary not of ignorance, but of causality. Silence is also a kind of data. The third horizon often discussed is the Hubble horizon. This horizon is defined by the rate of cosmic expansion itself. At a certain distance, the expansion of space causes galaxies to recede from us faster than the speed of light. This does not violate relativity because it is space expanding, not objects moving through space. The Hubble horizon marks the distance at which this recession speed equals the speed of light. The Hubble horizon is sometimes misunderstood as a hard boundary, but it is more fluid. Objects can cross it in either direction over cosmic time. Light emitted from beyond the Hubble horizon today may still reach us if the expansion rate changes. In that sense, the Hubble horizon is not as absolute as the cosmological event horizon. It is a snapshot of the universe's expansion at a given moment, not a final limit. Numbers whisper more than they speak. Together, these three horizons describe different aspects of our relationship with the universe. The particle horizon tells us how far our past observations can reach. The cosmological event horizon tells us which regions are permanently disconnected from our future. The Hubble horizon describes the current balance between distance and expansion. Each horizon answers a slightly different question, yet all are often folded into the single phrase edge of the universe. This is where confusion often arises. When people ask whether we might one day see beyond the edge, the answer depends on which horizon they mean. Some things have not yet been seen because their light is still on the way. Other things will never be seen, no matter how long we wait. The universe contains both kinds of unknowns, and physics treats them very differently. From a human perspective, this distinction carries quiet weight. We are used to believing that time eventually reveals all things, that patience is enough. But the universe does not always reward waiting. Some regions are not hidden because we arrive too early, but because we are causally separated forever. This is not a failure of curiosity. It is a consequence of living in an expanding universe with a finite speed of information. There is also a subtle shift in how we understand progress. Scientific discovery often feels like a steady expansion of knowledge, pushing back darkness step by step. Cosmic horizons remind us that knowledge expands unevenly. Some boundaries retreat as we learn more. Others remain fixed regardless of effort. The presence of permanent horizons does not diminish science, it defines its scope. As we learn to distinguish between what has not yet been observed and what cannot be observed, the idea of an edge becomes more refined. The universe does not present us with a single boundary, but with layers of limitation, each grounded in a different physical principle. Time, expansion, and causality each draw their own lines, and perhaps the calmest realization of all is this: not everything unseen is waiting to be revealed. Some parts of the universe exist without ever entering our story. They unfold without witnesses, complete in themselves. In a cosmos shaped by horizons, understanding does not come from crossing every boundary, but from recognizing which ones can be crossed, and which ones quietly remind us that not everything unseen will one day be seen. There is a quiet reason why some regions of the universe remain forever beyond our view, and it has little to do with the limits of human technology. Even with perfect instruments and unlimited patience, certain parts of the cosmos will never send us a signal. The cause is not distance alone, but the way space itself behaves over time. To understand this, we have to look not at how fast light travels, but at how quickly the universe expands beneath it. For much of the 20th century, scientists debated whether the expansion of the universe might slow down, eventually stopping or even reversing. In such a universe, given enough time, light from increasingly distant regions could eventually reach us. But observations over the last few decades have revealed something different. The expansion of the universe is not slowing, it is accelerating. Space is stretching faster today than it did in the past, and this acceleration changes what is possible to observe. When space expands, it increases the distance between galaxies. Light traveling toward us must cross that expanding space. If the expansion were gentle, light could make steady progress, gradually closing the gap. But when expansion accelerates, the distance light must travel grows while the light is already on its way. Beyond a certain point, the expansion outpaces the ability of light to compensate. The signal moves forward, but the destination recedes even faster. Space rarely gives us simple answers. This leads to a counterintuitive result. There are regions of the universe whose light is moving toward us right now, yet will never arrive. No matter how long we wait, the expanding space between us and those regions grows too quickly. Time, even if extended indefinitely, cannot overcome this effect. Waiting longer does not help if the underlying structure of space keeps increasing the separation. This idea challenges a deeply held assumption. We often believe that time is the ultimate solution to distance. If something is far away, we assume that patience will eventually close the gap. But in an accelerating universe, time alone is not enough. The geometry of space itself determines which connections are possible and which are not. The limit is not a matter of endurance, it is a matter of structure. Silence is also a kind of data. From a human perspective, this can feel strangely impersonal. We are used to thinking that progress depends on effort. Build a better telescope, collect data longer, improve sensitivity. These strategies work within certain bounds, but cosmic expansion defines a boundary that technology cannot cross. Even a detector capable of sensing the faintest imaginable signal would still receive nothing from regions beyond this horizon. There is simply no signal to detect. This does not mean those regions are inactive or empty. Galaxies continue to form, stars continue to burn, events continue to unfold. They simply do so without any causal connection to us. Their histories will never intersect with ours. They exist in the same universe, yet outside our observational story. Numbers whisper more than they speak. The realization that some limits are built into the universe itself invites a shift in perspective. It reminds us that science does not promise complete access to all of reality. Instead, it offers clarity about where access ends and why. Knowing that a boundary is fundamental is different from merely failing to overcome it. One is a temporary obstacle. The other is a feature of the universe. In this light, the unseen regions of the cosmos are not mysteries waiting to be solved. They are consequences of cosmic evolution. Their invisibility is not a gap in our understanding, but part of the understanding itself. The universe is not obligated to reveal everything, and observation is shaped by conditions that existed long before observers appeared. As we move forward, the idea of an edge continues to evolve. It is no longer something we imagine reaching. It becomes a quiet acknowledgement of the limits written into space-time. And perhaps the most calming thought is this: the universe does not hide its distant regions from us out of indifference or design. They are simply carried away by the same expansion that allows everything else to exist. To understand how the universe could be finite without having an edge, it helps to begin with shapes that feel familiar. Imagine a perfectly flat plane extending endlessly in every direction. In this kind of space, parallel lines never meet. Distances behave exactly as expected, and there is no natural boundary. This image has long shaped how people intuitively imagine the universe: infinite, uniform, and open. Yet flat space is only one possibility, not a requirement. Geometry allows for other structures that behave very differently, even while remaining complete. Now imagine the surface of a sphere. From close up, it can appear flat, just as the ground beneath our feet does on Earth. But as you move farther, the hidden curvature reveals itself. Lines that begin parallel eventually converge. Triangles have angles that add up to more than 180 degrees. Most importantly, the surface has a finite area, yet no edge. There is no place where the surface ends. You can walk in a straight line forever and never encounter a boundary, nor fall off into anything beyond. The surface is complete in itself. This simple comparison carries a powerful lesson. A something can be finite without being bounded. Our everyday expectation that finiteness requires an edge comes from limited experience, not from necessity. The surface of the Earth is not infinite, but it does not have a physical border where the world stops. It curves back on itself. The idea of a cosmic edge begins to soften once this possibility is taken seriously. Space rarely gives us simple answers. When cosmologists apply this reasoning to the universe as a whole, they consider higher dimensional versions of this same idea. Instead of a two-dimensional surface like a sphere, they imagine three-dimensional space that is curved in a similar way. This structure is often described as a hypersphere. It is not a sphere embedded in a larger space. It does not sit inside anything else. The curvature is intrinsic. Space curves within itself just as the surface of the Earth curves without needing an external reference. In such a universe, there is no edge and no outside. Every location is equivalent. There is no center and no privileged direction. Traveling far enough in one direction would eventually bring you back toward where you started, though the scale involved could be so enormous that this would never be practical to observe. From any local viewpoint, space would appear almost flat, especially if the curvature is gentle. This is why curvature can be so difficult to detect. Locally, it hides. Silence is also a kind of data. The absence of an edge in a hyperspherical universe challenges another deep assumption. We often imagine that if something has a shape, it must be embedded in something larger. A ball sits in a room. A planet orbits within space. But curved space does not require a surrounding container. Asking what the universe curves into is a misunderstanding of the geometry. Curvature here is not bending towards something external. It is a property of space itself. This idea is subtle and often uncomfortable. The human mind prefers layered explanations, inside and outside, here and beyond. But in higher dimensional geometry, these categories lose their usefulness. There is no external vantage point from which the universe can be viewed. There is no outside space waiting beyond the cosmos. The universe does not curve into anything. It simply has a shape. Numbers whisper more than they speak. The Earth analogy helps anchor this abstraction in experience. Long ago, people imagined the Earth as flat, bordered by edges or oceans beyond which nothing existed. The realization that the Earth is curved did not require finding an edge. It required noticing patterns. Ships disappearing hull first over the horizon. Different stars visible at different latitudes. Gradually, evidence replaced intuition. The surface remained the same. Only understanding changed. Cosmology follows a similar path. If the universe is curved, we may never encounter its full shape directly. We infer it indirectly, through patterns in light, through subtle correlations across vast distances, through the way geometry influences motion and structure. The curvature, if present, is likely so small that the observable universe represents only a tiny patch, much like a person standing on Earth sees only a small area that appears flat. This perspective reframes the idea of travel and limits. In a hyperspherical universe, there is no place where exploration ends in a dramatic way. There is no cliff, no boundary, no final destination marked by emptiness. Space continues smoothly without interruption. The absence of an edge is not a mystery to be solved, but a natural consequence of geometry that allows completeness without enclosure. For human understanding, this is both calming and demanding. It asks us to let go of the need for absolute borders. It suggests that the universe may be whole without being framed. That space can be finite without closure. That our instinctive questions may arise from the limits of perception rather than the limits of reality. As this idea settles, the notion of the edge transforms again. It becomes less about where space stops and more about how space is shaped. And in that shift, we may find a quieter kind of clarity. The universe does not need an edge to be complete. It needs only to be understood on its own terms, slowly, patiently, one curve at a time. As our understanding of the universe deepens, a quiet realization begins to emerge. The idea of an edge, so natural and intuitive to us, may not be a fundamental feature of reality at all. It may instead be a concept rooted in the way limited creatures experience space. We are beings who live and move within a small number of dimensions, navigating surfaces, rooms, and paths that always seem to end somewhere. From that perspective, edges feel inevitable. But physics is not obligated to respect the habits of human perception. The notion of an edge makes sense in low-dimensional environments. A line has endpoints. A surface can have a boundary. These are the spaces we interact with every day, and our language reflects that experience. We speak in terms of borders, limits, and outside regions because those ideas are useful locally. But as we move into higher dimensional descriptions of space, these intuitions begin to lose their authority. The universe does not scale up from a room or a field. It follows its own rules. In mathematics, particularly in topology, space does not require a boundary to be complete. A space can be finite and fully defined without having an edge at all. It can also be infinite without being open in the way we imagine. Topology concerns itself with properties that remain unchanged under continuous deformation. In this framework, the presence or absence of a boundary is not a universal requirement. Some spaces have edges, others do not. Neither case is more real than the other. It simply depends on the structure being described. Space rarely gives us simple answers. When physics borrows from these mathematical ideas, it does so carefully. The goal is not abstraction for its own sake, but clarity. If the universe is best described as a space-time manifold, then asking whether it has an edge becomes a question about the properties of that manifold. And in many well-defined models, there is no boundary. Space is not something that ends. It is something that connects back to itself or extends indefinitely without needing an endpoint. This leads us to a familiar question that sounds meaningful but may not be. What is outside the universe? The phrasing feels natural, almost unavoidable. Yet it assumes that the universe is an object embedded in a larger space. That assumption is precisely what modern physics has learned to question. If space itself is part of the universe, then the idea of an outside loses its footing. Outside is a concept that only applies when there is a container. Without a container, the word has no physical role. Silence is also a kind of data. This does not mean the question is foolish. It means the question may not correspond to anything real. In science, not every grammatically correct question has an answer. Some questions dissolve once their assumptions are examined closely. Asking what lies outside the universe may be like asking what time it is north of the North Pole. The structure of the question presumes a framework that does not exist. When the framework disappears, the question goes with it. For the human mind, this can be unsettling. We are conditioned to believe that every mystery must have an answer waiting somewhere, that if we push far enough, we will reach a final explanation. But physics often teaches a different lesson. Sometimes progress comes not from answering a question, but from realizing why the question no longer applies. This is not a loss, it is a refinement. Numbers whisper more than they speak. There is also a deeper humility embedded in this realization. The universe does not organize itself around the categories that feel comfortable to us. Concepts like inside and outside, beginning and end, edge and beyond emerge from our interaction with small-scale environments. They are tools, not truths. When applied beyond their proper range, they begin to mislead. In this sense, the disappearance of the edge is not a failure of understanding, but a sign of maturity. It marks the moment when we stop forcing the universe into familiar shapes and begin allowing it to define its own structure. Space does not need to satisfy our expectation of closure. It only needs to obey its own laws. As we continue this journey, the question shifts again. Instead of asking where the universe ends, we begin to ask how our language, intuition, and mathematics shape the questions we believe are worth asking. Some questions open doors, others reveal the limits of the room we thought we were in. And perhaps that is the calmest insight of all. Not every question is unanswered because we lack knowledge. Some questions fade because the universe gently shows us that they were never the right questions to begin with. If the universe is curved, the natural question follows quietly and persistently. Can we test it? Can we observe the shape of space itself rather than simply imagine it? In principle, the answer is yes. In practice, the task is extraordinarily subtle. Curvature on cosmic scales does not announce itself loudly. It leaves faint traces, patterns that must be teased out of vast amounts of data, often resting at the edge of what our instruments can reliably measure. One of the earliest places scientists looked for signs of curvature was the cosmic microwave background, the faint afterglow of the early universe. This radiation fills all of space and carries with it a record of conditions from a time when the universe was young and nearly uniform. If space were curved in certain ways, it could imprint repeating patterns on this background. Light traveling through a curved, finite universe might wrap around, allowing the same region of early space to be seen from different directions. In theory, this could appear as matching patches or repeated structures in the cosmic microwave background. Researchers have carefully searched for these kinds of repetitions, including concentric circles or correlated temperature patterns across widely separated regions of the sky. Such features would suggest that space closes back on itself, revealing a global curvature. The absence of clear repeated patterns does not prove that the universe is infinite. It only tells us that if curvature exists, it must occur on scales larger than what we can currently observe. Space rarely gives us simple answers. Another approach involves the large-scale distribution of galaxies. If space is curved, it subtly alters how volumes grow with distance. In flat space, the relationship between distance and volume follows familiar rules. In curved space, those rules shift slightly. By mapping the positions of millions of galaxies and measuring how their distribution changes across cosmic distances, scientists can infer whether space deviates from flat geometry. These measurements require patience and precision. Galaxies are not evenly distributed. They cluster, merge, and evolve over time. Separating the effects of cosmic geometry from the complex history of structure formation is a delicate process. The signal of curvature, if present, is small compared to the noise of cosmic evolution. Silence is also a kind of data. Over decades of observation, the results have been remarkably consistent. Within the limits of current measurements, the universe appears very close to flat. The angles of large cosmic triangles behave as expected in Euclidean geometry. The patterns in the cosmic microwave background align with predictions for flat space. The statistics of galaxy distribution show no strong evidence of global curvature within the observable region, but this conclusion is often misunderstood. Nearly flat does not mean infinite. It means that any curvature is gentle enough that it has not revealed itself within the region we can observe. A sphere with an enormous radius looks flat when examined locally. The Earth itself feels flat to someone standing on its surface. Only when measurements extend over large distances does curvature become apparent. The same principle applies to the universe. If its curvature radius is much larger than the observable universe, all current observations would still suggest flatness. Numbers whisper more than they speak. There are also practical limits that shape what we can know. Technology sets a ceiling on sensitivity. Instruments are affected by noise, both from the cosmos and from their own operation. Foreground signals from our galaxy must be carefully removed to isolate faint cosmological patterns. And perhaps most importantly, our observational reach is bounded by horizons. We cannot measure geometry beyond the region from which light has had time to arrive. These limits do not represent failure. They define the domain in which science operates. Precision cosmology has pushed measurements to extraordinary levels of accuracy, yet it still confronts questions that cannot be decisively answered with available data. The universe does not make its global shape easy to read. There is something quietly instructive in this. Science advances not by forcing certainty where none exists, but by learning how to live with carefully measured uncertainty. The statement that the universe is nearly flat is not a final verdict. It is a description of what the evidence allows us to say and no more. As we sit with this knowledge, the search for curvature becomes less about reaching a conclusion and more about understanding limits. The universe may be infinite, or it may be finite without boundaries. Both remain consistent with what we observe. The difference lies beyond our current horizon, in regions where geometry has not yet had a chance to speak to us, and perhaps that is enough for now. In the quiet balance between what can be measured and what must remain open, the universe invites patience. It reminds us that some truths emerge slowly, and others may always remain just beyond the reach of observation, not hidden, but waiting in the vastness of scale. There is a reason the idea of an infinite universe often feels uncomfortable, even to people who understand the mathematics behind it. The discomfort does not come from a lack of intelligence or imagination, it comes from biology. The human brain evolved to operate within a narrow range of scales, both in space and in time. It learned to measure distances in steps, arm lengths, meters, and eventually kilometers. It learned to track time in heartbeats, days, seasons, and years. These ranges were enough to survive, to plan, and to remember. Anything beyond them was unnecessary. Within those familiar scales, the brain excels. It can compare distances, estimate durations, and predict outcomes with impressive efficiency. But infinity does not fit into this system. It is not simply a very large number, it is a different kind of idea altogether. No matter how much we extend a distance or a duration, we never arrive at infinity, we only approach it conceptually. The brain, trained to expect completion, struggles with something that never resolves. Space rarely gives us simple answers. When confronted with the infinite, the mind often responds by trying to make it finite. It looks for an edge, a boundary, a final point where the counting can stop. This response is automatic. It brings relief. A universe with an ending feels manageable, even if that ending is unimaginably far away. A universe without one feels open in a way that resists closure. The discomfort that follows is not logical. It is emotional, rooted in the brain's desire for containment. Neuroscientists describe this tendency as a preference for cognitive closure. The brain seeks patterns that conclude. Stories have endings, journeys have destinations, problems have solutions. Infinity disrupts that rhythm. It offers no final scene, no resting point. The absence of an endpoint leaves the mind without a place to settle, and so it searches for one, even if physics does not require it. Silence is also a kind of data. There is a quiet irony here. The same brain that struggles with infinity can comfortably accept concepts that are equally abstract as long as they align with familiar structure. We can imagine billions of stars or trillions of galaxies, even though we cannot visualize them individually. Large numbers feel different from infinite ones because they still promise completion. Infinity does not. This difference matters when we talk about the universe. When scientists say that space may be infinite, they are not claiming that it is endlessly crowded with objects. They are describing a geometry without closure. Yet the brain often translates that statement into something more concrete, more crowded, more overwhelming. The emotional response comes from a misunderstanding, not of the math, but of what infinity actually means. Numbers whisper more than they speak. In the context of this journey, it helps to recognize that discomfort is not a sign of error. It is a signal that we have reached the boundary of intuitive thinking. The universe is under no obligation to conform to the scales our brains evolved to manage. When intuition falters, science does not demand forceful understanding. It asks for patience. This section of the journey is not about resolving the question of infinity. It is about noticing how we react to it. The unease, the desire for an edge, the impulse to imagine a final wall. These responses reveal more about human cognition than about cosmic structure. They remind us that understanding sometimes means accepting that certain ideas cannot be made comfortable. As the mind relaxes into this recognition, something subtle shifts. The need for an endpoint loosens. Infinity becomes less of a threat and more of a quiet backdrop. Not something to grasp, but something to allow. And perhaps that is enough for now. The universe does not ask us to feel at ease with its scale. It only asks us to notice where our instincts end, and to rest there, without forcing a conclusion. When people hear the word edge, they often imagine something physical. A boundary you could approach. A place where one region ends and another begins. In mathematics, however, the idea of an edge is far more flexible. It depends entirely on the structure being described. This difference between mathematical edges and physical intuition plays a quiet but important role in how we think about the universe. Consider a circle. It has a finite size. Its circumference can be measured. Its area is limited. And yet, it has no edge. There is no point on a circle where the line stops. You can move along it endlessly without encountering a boundary. The circle is complete without closure. This simple shape already challenges the assumption that finiteness requires an endpoint. It offers a calm reminder that edges are not mandatory, even in familiar geometry. Now consider the set of real numbers. It is infinite, extending without limit in both directions. Between any two numbers, no matter how close, there are infinitely many others. Yet this infinity is not chaotic. It has structure. It can be ordered, measured, and understood with remarkable precision. Infinity here does not mean absence of form. It means continuity without termination. The real numbers show that something can be endless and still deeply organized. Space rarely gives us simple answers. Topology takes these ideas even further. In this branch of mathematics, the focus is not on distance or measurement, but on connectivity. Shapes are studied based on how their parts relate, not how long or large they are. In topology, a space does not need an outside to be well defined. It does not need to sit inside anything else. A surface can be complete without reference to what lies beyond it. The concept of outside becomes optional, not essential. When physics adopts these mathematical frameworks, it gains new ways to describe space and time. The universe can be modeled as a manifold, a structure that locally resembles familiar space but may behave very differently on large scales. In such descriptions, asking where the universe ends may not be meaningful. The model is complete without an external reference. There is no missing piece. Silence is also a kind of data. This is where intuition often struggles. Our physical experience is dominated by objects embedded in larger environments. A table exists in a room. A city exists on a continent. We learn early that everything has an outside context. Mathematics gently shows that this need not always be the case. Some systems are self-contained. They do not require a surrounding space to make sense. The challenge is not that mathematics contradicts reality, but that reality may align more closely with mathematics than with everyday intuition. Physical intuition is shaped by small scales and practical concerns. Mathematics is free to explore possibilities unconstrained by survival needs. When these two perspectives meet, discomfort can arise. But discomfort is often a sign that new understanding is forming. Numbers whisper more than they speak. The difference between mathematical edges and physical edges invites a shift in how we frame questions. Instead of asking where the universe ends, we might ask how it is connected. Instead of seeking a final boundary, we might examine the rules that govern structure and continuity. These questions align more closely with the language physics now uses to describe the cosmos. There is a quiet elegance in this shift. The universe does not need an outside to be complete. It does not need an edge to be defined. Those requirements belong to the world of furniture and landscapes, not necessarily to space-time itself. As we settle into this perspective, the idea of an edge becomes less urgent. It fades from a demand into a possibility, one that may or may not apply. Mathematics does not insist that the universe fit our expectations. It simply offers a wider vocabulary. And in that expanded language, we find a gentle lesson. The limits we imagine are often reflections of habit, not of necessity. When we allow structure to replace borders, the universe feels less like a place that ends and more like a system that quietly holds together, complete without needing to be closed. For most of the history of astronomy, our understanding of the universe has been shaped almost entirely by light. Visible light first, then radio waves, infrared, ultraviolet, X-rays, and gamma rays. Each new window on the electromagnetic spectrum revealed something previously hidden, yet all of them shared the same limitation. They traveled at the speed of light, and they could only reach us from regions and eras where light was able to move freely. As powerful as light has been as a messenger, it is not the only one the universe provides. Long before the first atoms formed, before light could travel without being scattered, the universe was already active. Violent processes unfolded in its earliest moments, shaping its structure in ways that light could never record directly. To reach further back and perhaps further out, cosmology has begun to listen for different kinds of signals, ones that do not behave like light at all. One of these messengers is gravitational waves. These are subtle ripples in space-time itself, generated by accelerating masses. Unlike light, gravitational waves interact very weakly with matter. They pass through dust, gas, and entire galaxies with little disturbance. This makes them uniquely valuable as carriers of ancient information. In theory, primordial gravitational waves could carry imprints from the earliest fractions of a second after the universe began, long before the cosmic microwave background was released. Space rarely gives us simple answers. Detecting such signals is extraordinarily difficult. The waves are faint, and their effects are tiny compared to the noise of the universe around us. Yet even indirect evidence, subtle patterns in the polarization of the cosmic microwave background, may hint at their presence. If confirmed, these signals would offer a new way to study the universe, one that does not rely on light at all, but on the motion of space-time itself. Another messenger comes from particles rather than waves. Neutrinos are nearly massless particles that rarely interact with anything. Trillions of them pass through your body every second without leaving a trace. In the early universe, neutrinos were released long before light decoupled from matter. A cosmic background of neutrinos still fills space today, carrying information from an era that photons cannot reach. Detecting this neutrino background is even more challenging than detecting primordial gravitational waves. The signals are incredibly faint, and current technology is only beginning to approach the sensitivity required. Yet the promise is profound. Neutrinos could provide a direct glimpse into conditions that existed when the universe was only seconds old, offering a perspective unreachable by any telescope. Silence is also a kind of data. Together, these approaches represent a shift in how we practice cosmic archaeology. Instead of relying on a single type of signal, future cosmology may combine light, gravitational waves, neutrinos, and perhaps other messengers not yet imagined. Each carries a different piece of the universe's story, shaped by different interactions and limitations. Light shows us structure. Gravitational waves reveal motion. Neutrinos whisper of temperature and density from deep time. This expansion of methods does not replace traditional astronomy. It complements it. Light remains an essential tool, but no longer the only one. The universe is not obligated to speak in a single language. By listening in new ways, we may extend our reach not only farther in space, but deeper into the past. Numbers whisper more than they speak. There is a quiet humility in this transition. It acknowledges that our current picture is incomplete, not because we have failed, but because the universe offers more information than any single method can capture. Each new messenger expands the conversation, not by overturning what we know, but by placing it within a richer context. As we look ahead, the edge of observation becomes less fixed, not because the universe reveals everything, but because our ways of listening continue to evolve. Beyond light, beyond familiar signals, a new generation of cosmology is taking shape. And with it comes a calm reminder. The universe has been speaking since its beginning. We are still learning how to listen. When we think about the edge of the universe, we often picture a distant boundary in space. But there is another kind of edge that shapes our understanding just as profoundly. An edge in time. The universe is not only extended across vast distances, it is also stretched across an immense history, with its own beginnings and possible endings. To understand the limits of what we can know, we must consider both. The Big Bang represents the clearest example of a temporal edge. It is not an explosion in space, but a moment when space and time themselves emerged from a state we can no longer describe with ordinary physics. Looking back toward this beginning, we encounter a horizon of explanation. Our equations can trace the universe to a fraction of a second after its birth, but beyond that, the concept of time itself becomes uncertain. This is an edge of the past, not because nothing existed before, but because our current theories cannot reach further. It marks the limit of reconstruction, where evidence thins and models begin to overlap with speculation. Space rarely gives us simple answers. As we look forward, cosmology offers several possibilities for how the universe might evolve. Among the most discussed are the Big Freeze and the Big Rip. In a Big Freeze scenario, the universe continues expanding indefinitely. Galaxies drift farther apart, stars exhaust their fuel, and the cosmos grows colder and darker over unimaginable timescales. In a Big Rip scenario, expansion accelerates so dramatically that even bound structures are eventually torn apart. Though these outcomes differ in detail, they share a common theme. They represent edges of the future, states beyond which familiar structure no longer exists. These temporal edges shape not only the fate of matter, but the fate of information. As the universe expands, regions become increasingly isolated. Light from distant galaxies grows weaker and eventually disappears from view. Cosmic background radiation stretches and cools, fading into wavelengths that are ever harder to detect. Over time, fewer traces of the universe's early history remain accessible. Silence is also a kind of data. This leads to a quiet and often overlooked consequence. Observers living far in the future will have less information about the universe than we do today. Many of the clues that allow us to reconstruct cosmic history will have slipped beyond their horizons. The expansion that reveals the universe to us now will eventually conceal it from those who come later. In that sense, we inhabit a privileged moment. Not because we are central, but because we exist while the universe is still observable. Numbers whisper more than they speak. This idea reverses a common assumption. We tend to believe that knowledge accumulates steadily over time, that future observers will always know more than those before them. Cosmology suggests otherwise. Knowledge depends on access, and access depends on cosmic conditions. The universe is not a static archive. It is a changing environment, one that gradually erases its own records. From a human perspective, this realization carries a gentle weight. It reminds us that understanding is not guaranteed by time alone. It depends on circumstance. The Big Bang marks the edge of what we can reconstruct in the past. The long future of expansion marks an edge of what can be known ahead. Between these two edges lies a window, narrow on cosmic scales, in which observation is possible. This does not make the future bleak, it simply clarifies its nature. The universe is not moving toward an ending that is dramatic or sudden. It is moving toward quietness, toward isolation, toward a state where events still occur but leave fewer traces behind. The cosmos continues, but its story becomes harder to read. As we hold this perspective, the concept of an edge becomes more balanced. It is not only about where space might end, but about when information becomes unreachable. The edges of space and time are intertwined, shaping the boundaries of knowledge itself. And perhaps the calmest thought is this: we are not standing at the center of the universe, nor at its beginning or end. We are standing within a brief interval where the universe can still be seen, studied, and remembered. A moment between edges, where the past is visible and the future is still open. To understand where we are in the universe, it helps to imagine time not as a straight line, but as a slow, steady river. We are not standing on its banks, observing it from the outside. We are carried within it, moving forward moment by moment. Yet all of our observations point in only one direction, backward. Every telescope, no matter how advanced, looks upstream. Light arriving at our instruments began its journey long before it reached us, carrying messages from earlier moments in cosmic history. When we observe distant galaxies, we are not seeing what exists now, we are seeing what once was. In this sense, the present moment occupies a very special position. It's not simply the latest point in time. It is the crest of an observational wave. From here, we can see backward across billions of years, tracing the evolution of stars, galaxies, and cosmic structure. The farther we look, the deeper into the past we peer. The present becomes a narrow ridge between what has already happened and what cannot yet be seen. Space rarely gives us simple answers. This perspective reveals something subtle about how knowledge works in cosmology. The universe does not allow us to look ahead. The future emits no light, no signal, no information that can travel backward to reach us. The river of time flows in one direction only. While physics can model possible futures, observation itself is confined to what lies upstream. The future remains inaccessible, not because it is hidden, but because it has not yet occurred. Silence is also a kind of data. Because of this asymmetry, the present moment becomes uniquely valuable. It is the point at which the maximum amount of information is available. Enough time has passed for light from the distant past to arrive, but not so much time that cosmic expansion has erased those signals from view. We live at a moment when the universe is still readable. The cosmic background radiation is still detectable. Distant galaxies are still visible. The large-scale structure of space has not yet faded into darkness. This will not always be the case. As the universe continues to expand, more regions slip beyond observational horizons. Light stretches, weakens, and disappears. Future observers may find themselves surrounded by darkness with fewer clues about the universe's origin. Their sky may hold only a single galaxy, or none at all. The cosmic story will not have changed, but access to it will. Numbers whisper more than they speak. From a human point of view, this realization carries quiet meaning. We often assume that progress moves in one direction, that future generations will always know more than the past. In cosmology, the opposite may be true. Knowledge is shaped by cosmic conditions, not just intelligence or effort. The ability to see the universe depends on when you exist within it. This does not make our moment special in a dramatic sense. It makes it fragile. We are here during a brief interval when observation is still possible on the largest scales. The universe has aged enough to reveal its structure, but not so much that it has concealed it again. This window is wide enough to study, but narrow enough to be missed entirely. As individuals, we experience time as fleeting. Moments pass quickly. Years seem to shorten as we age. On cosmic scales, our entire civilization occupies an almost immeasurably small slice of the timeline. And yet, within that slice, we have access to a vast portion of the universe's history. We can see back to the first light. We can map billions of galaxies. We can reconstruct the past with remarkable detail. This perspective invites a quieter form of reflection. We are not at the beginning of time, nor near its end. We are somewhere in between, carried gently along the current. Our instruments look backward, our theories reach forward, and our understanding forms in the space between. Perhaps the calmest way to see our place is this. We are living at a moment when the universe can still be seen, still be studied, still be remembered. Not because we are central, but because the river of time happens, for now, to pass through a place where light still reaches the shore. As we move closer to the deepest questions about the universe, another kind of edge quietly comes into view. Not an edge of space or time, but an edge of knowledge itself. Science has extraordinary reach, yet it is guided by a small number of firm principles. At its core, science depends on observation and verification. Ideas must be connected in some way to evidence. Hypotheses must be testable, at least in principle. When those conditions fade, science does not abruptly stop, but it begins to thin, blending into neighboring ways of understanding. This boundary is not a failure of science, it is one of its defining strengths. Science is careful about where it claims authority. It does not ask us to believe without reason. It asks us to observe, to measure, and to check. When a theory makes predictions that can be compared against the universe itself, it earns its place. When it cannot, it remains provisional, suggestive, or incomplete. In modern cosmology, some of the most intriguing ideas live close to this boundary. Concepts such as eternal inflation or the multiverse arise naturally from certain mathematical frameworks. They are internally consistent. They solve problems elegantly. They extend known physics in ways that feel coherent and even inevitable. On paper, they are beautiful. Space rarely gives us simple answers. Yet beauty alone is not enough. The challenge with these ideas is not that they are implausible, but that they may lie beyond direct verification. Other universes, if they exist, would by definition be causally disconnected from ours. Eternal inflation may operate on scales far beyond any observable horizon. The mathematics works, but the universe does not easily provide a way to confirm or deny these claims through observation. This places such ideas in a delicate position. They are not pseudoscience, they are grounded in serious theoretical work, but neither are they fully empirical science in the traditional sense. They occupy a gray zone, where reasoning is strong but evidence is indirect or absent. This does not invalidate them. It simply limits what can be responsibly claimed. Silence is also a kind of data. At this edge, the role of humility becomes central. Science advances by knowing not only what it can say, but also what it must leave open. The temptation to push beyond evidence is understandable. The universe invites curiosity. It encourages speculation. But science remains careful, drawing a line between what is suggested by theory and what is confirmed by observation. This is where philosophy quietly enters the conversation. Philosophy asks questions about meaning, about assumptions, about the structure of explanation itself. It helps clarify what we mean by concepts like existence, causality, and infinity. When science reaches its observational limits, philosophy does not replace it, but it helps frame what remains uncertain. And beyond philosophy, there is another layer still. A way of speaking about the universe that does not aim to prove, but to reflect. To gesture rather than conclude. This is where poetic language often appears, not as decoration, but as a response to scale. When the universe grows too large, too old, or too abstract for direct testing, metaphor becomes a bridge, not a substitute for science, but a companion to it. Numbers whisper more than they speak. The boundary between science, philosophy, and what might be called cosmic poetry is not rigid. It shifts as knowledge grows. Questions that once belonged to philosophy alone, such as the age of the universe or the nature of space-time, have moved firmly into science. Other questions may one day follow. What lies beyond the observable universe? Why physical laws have the form they do? Whether reality has multiple realizations? These questions hover at the edge, waiting for new ways to be asked. It is important to notice that stopping short of certainty is not the same as giving up. Science does not promise final answers, it promises reliable ones within defined limits. When those limits are reached, the honest response is not to fill the gap with certainty, but to acknowledge it openly. For the human mind, this can feel unsatisfying. We are drawn to complete stories. We want beginnings and endings. We want explanations that close the loop. But the universe does not always cooperate. Some questions remain open not because they are poorly formed, but because the tools required to answer them may not exist yet, or may never exist at all. There is a quiet strength in recognizing this. It allows science to remain grounded, and it allows wonder to remain alive. The edge of knowledge is not a wall, it is a shoreline. Beyond it lies speculation, imagination, and reflection. Not as enemies of science, but as different ways of engaging with the unknown. As this journey slows, the question of where science ends becomes less urgent. What matters more is how carefully it approaches that ending. With patience, with restraint, with respect for evidence and for silence. And perhaps the calmest understanding of all is this: science does not fail when it reaches its edge. It simply pauses, leaving space for thought, for humility, and for the quiet recognition that some aspects of the universe may always remain just beyond the reach of proof, inviting us not to conclude, but to continue listening. As we come to the end of this journey, it becomes clear that the edge of the universe is not a destination we arrive at. There is no wall waiting at the farthest distance, no final boundary where space simply stops. The universe does not present us with a dramatic ending point, marked by emptiness or silence. Instead, it offers something quieter and more subtle. It offers horizons. Throughout this exploration, the idea of an edge has slowly shifted. What once sounded like a physical limit has revealed itself as a set of conditions, a horizon of light, beyond which signals have not yet arrived. A horizon of time, beyond which the future cannot be observed and the deepest past cannot be fully reconstructed. And a horizon of understanding, shaped not only by the universe itself, but by the minds attempting to comprehend it. Space rarely gives us simple answers. There is no final place to reach because the universe is not a path with an endpoint. It is a structure that unfolds according to its own rules. What we encounter are origins, where familiar explanations begin to thin. What we encounter are limits, not of existence, but of access. These limits are not permanent walls. They are temporary boundaries defined by time, expansion, and perspective. As conditions change, horizons shift. Knowledge grows, pauses, and grows again. When we speak about the edge of the universe, we are really speaking about three edges at once. The edge of light, where information has not yet had time to reach us. The edge of time, where our models lose contact with evidence, either in the distant past or the far future. And the edge of human understanding, where intuition gives way to abstraction and certainty gives way to careful silence. Silence is also a kind of data. There is something quietly reassuring in this realization. The universe does not demand that we understand it completely. It does not require closure. It allows partial understanding, gradual insight, and unanswered questions to coexist. In a cosmos this vast, knowing everything was never the goal. Learning how to listen was. Numbers whisper more than they speak. For human beings, this perspective invites a softer relationship with knowledge. We are not explorers racing toward a final frontier. We are observers, situated within a brief and meaningful window of time, during which the universe is still visible, still speaking through light and structure. Our instruments look outward, our theories reach inward, and between them lies a space for reflection. As the night deepens, the questions do not need to be resolved. They can remain open, suspended like distant galaxies whose light continues to travel. Understanding does not arrive all at once. It settles slowly, often without words. The edge of the universe, in the end, is not where meaning stops. It is where certainty softens, where curiosity remains, but urgency fades, where the need to explain gives way to the willingness to observe. And perhaps that is enough. The universe does not ask us to grasp it fully. It only asks that we remain attentive, quiet enough to notice, patient enough to wait, and calm enough to let the unanswered questions drift gently as we do into rest.